And thanks to all the organizers for creating such a great program for the rest of this week, and also such a great program for the whole trimester. So I'm going to talk about joint work with Jack Thorne on symmetric power functoriality for Hilbert modular forms. And I'll just start out with a brief sort of introduction and statement of our results. So let's just start out with a number field F. And some cuspidal automorphic representation pi DL2 of B delta F. I might sometimes abbreviate cuspidal automorphic representation to CAR for short. Convenient. I mean, CARs are not always convenient, but this abbreviation will be convenient. And then we have conjecture of Langlands. Special case of a functoriality conjectures. It's going to say that for an integer n at least 2, there exists an isobaric automorphic representation, which will be the n minus first symmetric power lifting of pi. And well, I'm doing the n minus first lifting, so what I get will be an automorphic representation of GLN. Here delta of F. Okay. And the idea is that on the L parameter side, this corresponds to just composing the two-dimensional L parameter for pi with the n minus first symmetric power of a standard representation. So one way to describe that is with the local Langlands correspondence. So if I take a place V of F, I'm going to characterize this automorphic representation by describing its local factors. And I'm going to describe those local factors by saying what they should match up with under local Langlands. This rec is going to be the local Langlands correspondence. The GLN over FV. Okay, so that's going to give me a n-dimensional L parameter, and that should match up with the local L parameter for pi when we push forward by the n minus first symmetric power of the standard representation. It's sim n minus 1. Standard. It's an n-dimensional representation of GL2. Right, so that's a conjecture. And I mean, maybe one reason why this is a particularly interesting case of Langlands functoriality conjectures is if you can prove this for all n, then you've kind of understood these functorial transfers along all the kind of irreducible representations of GL2. So that gives you a lot of information about the sort of L functions for this automorphic representation pi. All right, so let me say a theorem. So for our theorem, we have to sort of restrict the setting a bit, so we're in a world where we have Galois representations. So, yeah, I guess our paper went on the archive at the end of last year. Now I assume F is totally real, and that pi is regular algebraic. I'll say a word about that in a minute. And finally, just to sort of exclude some degenerate cases, I'll assume pi is not an automorphic induction from a quadratic extension of F. So in other words, pi is not a sort of CN. Okay, so with these assumptions, we prove that this symmetric power lifting exists. And it's also cuspidal. That's the reason for excluding these CN cases, just so we make sure we get a cuspidal automorphic representation in the end. So a little bit like this regular algebraic. It's, in this case, sort of equivalent to cohomological. So in this context, that basically means that pi is going to contribute to the cohomology of the Hilbert modular variety. Okay, and then sort of in more classical language, in terms of Hilbert modular forms, this regular algebraic condition is going to mean that sort of pi up to twist comes from a holomorphic Hilbert modular form. Those things have weights, which are tuples of integers. And a regular algebraic condition is going to say that those weights are all at least 2. And that they have the same parity as well. All right, and just to repeat, I already kind of mentioned the reason for this regular algebraic condition is that these are the kinds of holomorphic Hilbert modular forms where we have a compatible family of Gower representations associated to. Yes, thank you. Okay, is that good for everyone? Yeah. Okay, so that's the theorem. Let me give you a tiny bit of history. So you talk about in what cases this full conjecture is known. So that's for arbitrary number fields, arbitrary types of automorphic representation pi. In that case, we have the sort of symmetric square functoriality. So that's n equals 3 with my notation. So this was proved by Skelbarth and Jack following some work of Schumacher. I think this happened in the 70s, really quite soon after Langlands set out his functoriality conjectures. And then much later, there was work on the symmetric cube and symmetric fourth power. Him and Shahidi, the cube, and then him with the fourth power. That's in 2002. As I said, these results are kind of completely general. Of course, they don't use Gower representations in any way. And well, one of the essential ingredients are converse theorems. But these are kind of, I mean, especially these later works, is a very kind of delicate thing. It involves something to do with Eisenstein series on exceptional groups. More recently, there was sort of progress in the setting of the theorem, so in this regular algebraic setting. So there were results on potential automorphy. following work of Clausel, Harris, Taylor, Shepard-Barron. It's the, I'm going to state, was proved by Barnett, Lamb, G and Geraghty. In something like 2011. And they proved that this symmetric power lifting exists at least over some auxiliary extension field. So we have to fix the n. So we're going to look at the n minus first symmetric power lifting. And they showed there exists some extension field, Fn over F, which will depend on n, as the notation suggests, or could depend on n. We have this extension field, and then they sort of produce the lifting, but only over Fn. Let me kind of suggestively write sim n minus 1 pi Fn. So we knew that sim n minus 1 pi existed, and if we could do a sort of base change functoriality for an arbitrary extension like this, then this automorphic representation would be the base change of the symmetric power lifting. Yeah, so let me just sort of say it matches these L parameters. Yeah. Oh, good question. Does it depend on pi? I think so. I think it depends on pi. Yeah. All right, and it's going to match these n-dimensional L parameters. Course, now because we've done this base change, we're going to restrict them. To a local Vey group at a place dividing place B.
Maybe it depends on what the reduction of powers.
Yeah, it's why I hesitated. You can probably, you can say something interesting along these lines. Thanks. All right, and well, this result it falls a bit short of Langmuir's conjectures, but it's already very important because this gives enough information to prove the Sartor-Tate conjecture for pi. About the distribution of its Sartor-Tate parameters. Get some new chalk. Right, so I'll talk about something that's a bit more directly related to the content of the rest of my talk, which is some work of Clausel and Thorne. And a series of 3 papers, mid-2010s. Okay, so they proved this theorem about existence of symmetric power lifting for small values of n. So n at least at most 9. That goes up to the 8th symmetric power. And well, I'm going to say much more about their strategy later because that's the strategy we're going to follow to prove our main theorem. Yeah. I'll mention this later as well. Yeah. Thanks. Okay, and then more recently, Jack and I maybe 2020, 21, something like that, proved the theorem when f equals q. So for elliptic modular forms. And we used a different strategy to the Clauzel-Thorne strategy. There are some commonalities, which I'll try to discuss a bit during the rest of the talk. Yeah, but we did use a different strategy, but really didn't generalize to any totally real field, any extension of Q, as far as we know. So it doesn't generalize because it relies on some special properties about two-adic modular forms in tame level 1. The same way that sort of Parent-Van-Berger's proof of the Serre's conjecture relies on some kind of coincidences about small primes and discriminant bounds. So yeah, we couldn't push this strategy to more general totally real fields. All right, so that's the introduction. The next thing I'm going to do is sketch the strategy of Clauzel-Thorne. Okay. So at this point, I'm going to introduce some Galois representations. Right, CT for short, for Clauzel-Thorne's papers. So we've got R pi as in the theorem, it's regular algebraic automorphic representation of GL2AF. That means it has a compatible family of Galois representations associated to it. So for every prime P, and isomorphism iota from UP bar to C, I have a Galois representation R pi iota of the absolute Galois group of totally real field F with coefficients in UP bar. Yeah, so this is my, if you like, global L parameter for this automorphic representation. And of course, this is characterized by the sort of image of Frobenius matching the Satake parameter of pi at unramified primes. Okay. And now in terms of the Galois representations, what we need to do to prove the theorem is kind of clear. We just have to look at the n-dimensional Galois representation we get by applying n-1 representation to GL2. And we just want to prove that comes from an automorphic representation of GLN. Well, we can sort of easily translate this problem of functoriality into one of Lang's reciprocity. And then the idea of Clauzel-Thorne is to exploit the kind of reducibility of this symmetric power representation in small characteristics. Okay, so we're going to choose a prime P. Which is in between n/2 and n. You can do that by Bertrand's postulate, proved by Chebyshev. Now, what happens if we look at this sim n-1 representation in characteristic P? So we can think about representations of GL2FP bar. If you look at the standard two-dimensional representation of this group over FP bar, we can take its n-1st symmetric power. And because n is bigger than P, I'll get something reducible when I do that. If you take its semi-simplification, you can compute the irreducible constituents. So you get the standard representation with a Frobenius twist, arithmetic Frobenius twist. So this is a two-dimensional representation of GL2FP bar, where the matrix is actually going to act via, you apply this automorphism phi, and then you act in the standard way on FP bar squared. Okay. We see that Frobenius twist of a standard representation tensored with a smaller symmetric power representation in n-1 minus P. Okay, so that's one of the irreducible factors. And then the second irreducible factor is another smaller symmetric power representation. The 2p minus n minus first symmetric power of the standard with a determinant twist. Okay. So this is a sort of computation you can do in the representation theory of these algebraic groups in positive characteristic. And well, because we chose P carefully to be in this range between n/2 and n, that means these two factors of themselves are going to be irreducible. Yeah. And they're going to be sort of proper subs of this semi-simplified representation. Okay. Now let me say a bit more about how Jack Thorne proposed to use this. So this sort of reducibility in characteristic P means that if we take our p-adic Gauss representation, R pi iota, and pick a sort of Galois stable lattice and reduce modulo P, then we'll end up with a reducible mod P Gauss representation. We'll write something corresponding to that. When I write this overline, I mean, you do the sort of semi-simplified reduction. So that will give me a two-dimensional FP bar representation. And you can take its n-1 symmetric power. Maybe I should have semi-simplified that as well. Anyway, it's not so important. So everything is up to semi-simplification. And I'll get a reducible mod P representation here, where these factors exactly correspond to the decomposition I wrote on the board over there. We just note their dimensions. So, this factor will have dimension 2 times n minus p. This one will have, of course, the complementary dimension, which is 2p minus n. Right. Now, what is their strategy? Yeah. So we've got 2 smaller dimensional mod p Garrett representations here. The first part of the strategy is going to be to prove that those are automorphic. They arise as reductions of automorphic Garrett representations. Okay. So what that will do is give us 2 automorphic representations, one of GL 2n minus p, one of GL 2p minus n. So that if I take the Langlands direct sum, I get a non-cuspal automorphic representation whose mod p Garrett representation matches this symmetric power. So that's good. We've got some kind of input. We've got some kind of congruence to an automorphic representation. And then the next step, which is actually at the sort of heart of what Clazel and Thorne actually prove in their series of papers, is called level raising. So this sort of Eisenstein automorphic representation is not going to be good enough to carry out a strategy. We're going to have to find a congruence to a cuspidal automorphic representation with specific properties at some auxiliary local place. That's what the level raising will be. But,
Are you going to say more about it?
yes. Okay. Find congruence mod p from this Eisenstein thing to some cuspidal thing. All right, big pi. And then the point of doing step B is that we'll then be in a situation where we can hope to apply an automorphy lifting theorem. Change chalk again. So that's the outline of the strategy. I'll just sort of say a bit about how one actually carries out these steps. Let me start with B. Well, I'm not going to tell you anything about how to actually do it. I'm just going to say that it has been done. So as I mentioned, this level raising congruence gets proved in some cases in Clazel and Thorne. They just sort of do a sort of restricted number of cases, which is one reason why there's this sort of n less than or equal to 9 restriction in their main theorem. And then more recently, Thorne proved much more general level raising result that gives the sort of necessary input for part B of this strategy in general. So that sort of completes the level raising part of this Clauzel-Thorne strategy.
But doesn't this require, there's some hypotheses require 1 by 2?
There's all kinds of hypotheses, yeah. So I'm sweeping under the rug that we're going to assume things are ordinary, because in the end we're going to apply an ordinary automorphy lifting theorem here. The level raising is going to be for, yeah, very specific kinds of level raising congruence. Yes, throughout the talk, I'm afraid there's going to be a lot of hypotheses swept under the rug.
There's no hypothesis on the reduction of the Calvert limitation. Okay.
In the theorem?
In the main theorem.
Yeah, no, the main theorem I correctly listed the hypotheses. All right. Yeah, step C, apply an automorphy lifting theorem. So, as I mentioned, something I'm sweeping under the rug is that we'll be able to put ourselves in a situation where pi is ordinary. And then we have available some automorphy lifting theorems, which apply in this sort of residually reducible case. So let's call these Skinner-Wiles type. Lifting theorems. So Jack proved one of these, which was used in his work with Clauzel, and then with Patrick Allen, we proved a slightly more flexible version of this automorphy lifting theorem. So that's A and so that's B and C, and the main point of the second half of today's talk is going to be to explain how we do step A. So step A is about showing automorphy of these summands of the residual representation. Let me remind you what these summands look like. They're kind of written on the board above here, but just in terms of the algebraic representation of GL2. We need to prove automorphy of, we've got a Frobenius twist of our mod P representation. So I'll just abbreviate R pi iota bar to R bar from now on. So this is a two-dimensional mod P representation. So that's our twist, and then we tensor with a symmetric power. And then our other summand is a determinant twist of a symmetric power. So we need to prove these two pieces are automorphic. And the second one, we're in good shape because it's going to give us access to an argument that inducts on n, that inducts on the symmetric power. Okay, this one is a smaller symmetric power than the n minus first one, which we started with. So we can handle that piece by induction on n. Sorry, say again. What is rho? Ah, it's R. Thank you. Thanks very much. Okay, and then the other piece is to be the problematic one. So I have one symmetric power factor, which I can assume is automorphic by induction on n. But then I'm tensoring it with a two-dimensional representation. So what we actually need to carry out this Hausdorff strategy is we somehow need some cases, at least, of tensor product functoriality. So we need to know if we tensor a two-dimensional representation, or this particular two-dimensional representation, with this n minus p dimensional representation, that we get an automorphic Gauss representation. And yeah, for the Hausdorff form, we're able to carry out the strategy in some cases, because if this second factor has dimension at most 3, then we know the tensor product functoriality for GL2 times GL3 to GL6, for example. So that's the theorem of Kim and Shahidi. There's also Ramakrishnan proved the sort of 2 by 2 dimensional tensor product functoriality. So at this point, we're kind of okay if we can choose our prime p so that n minus p is less than or equal to 3. So to go further, we need to prove something about automorphy of these tensor products. Maybe section 3. And the first step, the first kind of tensor product we're going to be able to show is automorphic. It's going to use the same idea of Thorne about exploiting reducibility of some algebraic representations. What I'm going to do is I'm going to forget about the Frobenius twist that appears in this Gauss representation, which I'm interested in. So I'm just going to look at R bar, not the Frobenius twist. And I'm going to tensor product with, let me just simplify my notation a bit. So it's going to be the m minus first tensor product. So m here will be n minus p, and it's going to be in the range from 0 to p. So now if I take the standard representation and I tensor product with a symmetric power of a standard representation, I get a reducible algebraic representation, even in characteristic 0. An exercise in Fulton and Harris to work out what you get. We're going to get the nth symmetric power plus a determinant twist of the m minus second symmetric power. Okay. So again, we get a reducible representation. Now the factors are still smaller symmetric powers than the symmetric power we were interested in to begin with, sim n minus 1. So we can argue by induction that these two pieces are automorphic. And then what we could do is try and carry out a version of this Thorne idea. So what we can do is sort of use an automorphy lifting theorem for a residually reducible representation again. What we can get is automorphy of certain characteristic zero representation. So we're going to have R pi iota, the p-adic representation we started with. And then we're going to tensor with the m minus first symmetric power of a different automorphic Gauss representation called R sigma iota. And we can do this for a certain sigma, which is congruent to pi modulo p. You might ask why we can't just take sigma equals to pi there. Well, because this reducibility of the algebraic representation held even in characteristic zero, that would give us a reducible characteristic zero representation there, which we can't apply these automorphy lifting theorems to. Okay. So we can choose sigma so that this characteristic zero representation will be irreducible, but it's still congruent modulo p to the reducible representation on the previous board. That gives us automorphy of this untwisted tensor product. And then the problem is to try and get to automorphy of the twisted tensor product. So let's rearrange slightly. I'm going to think about how we might hope to get from automorphy of this untwisted tensor product to automorphy of a tensor product with the Frobenius twist, which is what we really need. Section 4. Okay. So what's the kind of setup? We can choose a Frobenius lift in the absolute Dow group of QP, lifting our arithmetic Frobenius. And then we would be happy win if we can prove automorphy of the, we apply this Frobenius lift to the coefficients of our two-dimensional Gauss notation. So that gives us a two-dimensional twist. And then we tensor with our m-dimensional piece. In the end, this is what we want to try and do. We've got a tensor product like this. We want to prove it's automorphic, and we know automorphy if we just delete this twist. All right, so yet again, we're going to apply some automorphy lifting theorems to get from automorphy of the untwisted tensor product to automorphy of the twisted product. A bit about how we could sort of hope to do that. Then maybe at the end, I'll say a tiny bit about the kind of automorphy lifting theorem we have to apply. If we want to apply an automorphy lifting theorem, we have to find some sort of chain of congruences connecting two compatible families of Gauss representations. These two Gauss representations we're interested in, they're certainly not congruent modulo P, so we're going to have to work in the compatible family and look modulo some other primes. Let me explain how we do that. So we've got this Frobenius lift. By tilde, and then we've also got our isomorphism iota and QP bar to C. So using that, we can match up phi tilde with a automorphism of C. I'll call gamma. And this twisted two-dimensional Gauss notation is it's the same as taking the Gauss notation coming from kind of gamma conjugate of pi. The sort of thing proved by Clauzel for regular algebraic automorphic representations. You can conjugate automorphic representations like this, regular algebraic ones, and get another regular algebraic. You've got some Frobenius eigenvalues, they're algebraic. You can apply gamma to those Frobenius eigenvalues. Clauzel is telling us that those are Frobenius eigenvalues of a different automorphic representation. And this conjugate only depends on how gamma acts on the coefficient field of pi. So there's some finite extension of Q, where all the Frobenius eigenvalues for pi live. I can take a Galois closure, so it's really is in a Galois group of a number field. So here, E pi is the Galois closure. The coefficient field of pi. All right. And then the sort of cute trick we use is that this Galois group of a number field over Q is generated by its inertia subgroups, because there are no everywhere unramified extensions of Q. So you could write gamma as a product of some elements delta in this Galois group. Each of these will live in an inertia subgroup for some place Wi of the coefficient field E pi, living over some rational prime Li. Decompose this twist gamma into a product of inertial elements. And just for simplicity, I'll assume that we just have one. You can sort of repeat the argument if there are more than one. Let's assume gamma is in one of these inertial subgroups. Okay. So now what can we do? Well, we've got a place W of the coefficient field. So we can choose an isomorphism iota L from QL bar to C, which induces that place W on the coefficient field, which lives inside C. Then we can also choose gamma L in the inertia group inside that absolute Galois group of QL, which lifts gamma. Okay. And now what happens is that if we look at our gamma conjugate of pi and look at its associated L-adic Galois representation, defined using this isomorphism iota L, then what I get will be just given by applying gamma L to the coefficients of the L-adic Galois representation coming from pi. So if you just sort of trace through what happens to the conjugated automorphic representation versus doing sort of acting on the coefficients of a Galois representation, you'll find that these two Galois representations match up. Okay. And now the fact that gamma is in the inertia subgroup is crucial because that's going to give us a congruence. It means it acts trivially on the residue field. So when I look at the mod L reduction of this Galois representation, it's going to be the same as the untwisted Galois representation. That gives us a congruence mod L from our twisted Galois representation to our untwisted Galois representation. Okay, so I guess I have about 5 minutes left. So is that right, Anna? Yeah. So that time I'll just sort of sketch how we actually apply an automorphic lifting theorem to use that congruence. Any questions? Now the idea is to exploit this congruence, this mod L congruence, using what we call a functoriality lifting theorem. I'll just sort of tell you what the sort of shape of this theorem looks like without giving you the technical hypotheses, of which there are many. So I'm going to have a prime L. I'm going to have two-dimensional elliptic representations, R and R primed. So these will be, in the application, these will be R pi iota and, R pi iota L, it's an elliptic representation. And then we also have this twist by gamma L of R pi iota L. Those will be R and R prime respectively in the application. And then there'll be an m-dimensional representation okay. And that one will be m minus first symmetric power, which we're tensoring with. I'm going to have these three Gauss representations. I'll assume that all of them are automorphic. And I'm going to assume I have a congruence modulo L between R and R primed. And well, the reason why we call it a functoriality lifting theorem is I'm going to assume that I already have a sort of functorial lift for one of my pairs of representations. So I'm going to assume that R tensored with S is automorphic. Then the conclusion is that the congruent representation is automorphic. So R primed tensored with S is automorphic. That's the sort of shape of the theorem. And phrased like this, I mean, it looks like just a sort of special case of every other automorphic lifting theorem you've ever seen. There's an automorphic representation here. It's congruent to this representation. So we propagate automorphy from R tensor S to R prime tensor S. But what we're able to do with this kind of slightly more elaborate setup, where we have this sort of tensor product functoriality that we're paying attention to, is that we can prove this with quite weak technical hypotheses. So it's probably quicker to list some things which are not technical hypotheses than to list the technical hypotheses themselves. So things which are not hypotheses are that the reduced representation R bar tensor S bar can be reducible. And this is not a sort of Skinner-Wiles type thing because we don't have to make any ordinary hypotheses. So those things in combination make this more useful than previous automorphy lifting theorems in this context. And yeah, I'm basically done. So I'll just very briefly mention the proof involves doing sort of patching a la Taylor-Wiles and Kiss in the sort of two-dimensional setup. But then to control what's happening with our 2m-dimensional representations, we use vanishing of an adjoint Selma group that was proved in a kind of different way. All right, that's it. Thanks.
Are there any questions?
Yeah.
Can you say a bit more about how you arrange the association to group your connections of ordinary?
So I was asked why we can sort of restrict to ordinary representations when we apply these residually reducible automorphy lifting theorems. So when we're trying to prove automorphy of a symmetric power, you're free to kind of, instead of proving automorphy of a symmetric power of a representation you started with, you can find a congruence modulo a big prime to something else, and then apply some automorphy lifting theorems that work when you have sort of big image residually. So there's quite a lot of flexibility. So we're also allowed to do a sort of solvable base change. So what you need to do is just find some big prime and some solvable extension of f, where you can find an ordinary representation that's congruent to the one you started with. So actually, you can even arrange that the representation is like chronological weight 0 and Steinberg at your favorite place. We want it to be ordinary at P, but we can find the congruence modulo some completely different prime. So we prove a theorem for polarized representations over CM things. Yeah, but in the non-polarized case, I think we're a long way from carrying out any part of the strategy, basically. Yeah, in fact, it's already in Clazel-Thorne's third paper. They prove a theorem for the sort of total real fields case, and then they just deduce the polarized CM field case. It's a clever trick by congruences again. Yeah, so that's already in Clazel-Thorne. And once you have the polarized CM field case, you can actually get rid of this restriction on the parity of the weights of the Hilbert modular form. There's this sort of argument of, like, it goes back at least to Blazes and Ramakrishnan, where you can sort of twist by a character and restrict to a CM extension to get yourself into a situation for proving automorphy over a CM field instead.
Other questions?
I think for Hausdorff where to reduce the condition where n is smaller or equal than.
Yeah, so
Maybe repeat.
the question was, in Clazel-Thorne they had this condition that n is less than or equal to 9. So once Thorne proved a more general level raising result, their methods actually went a bit further. So Thorne actually proves, for example, I think the biggest power is the 25th symmetric power. So you can get automorphy of the 25th symmetric power just using what's already in their sort of strategy. And that's exactly because you need to be able to choose these primes so that n minus p is less than or equal to 3. And then you do an induction, so you need to sort of keep on being able to choose the primes between n over 2 and n, where the difference is less than or equal to 3. Yeah, so if you try and do this for n equals 28, I think it won't work, because the nearest prime to 28 is 23. Yeah, so that's bad, right? N equals 28. I'm happy. 27, you think that doesn't work either? Yeah, quite possibly. Yeah, I was thinking about either. I think for odd n, if the problem comes earlier, maybe. Yeah. Thanks for the question.